It gives me great pleasure to introduce James Gosling. We were just talking over there in the corner. It's like been 29 years when we first got together at Sun. So, but that's old history. Let's talk about the new stuff, liquid robotics. James Gosling.
So for the last 2.5 years, I've been working at this funny company down in Sunnyvale called Liquid Robotics, and as the name would imply, we make robots that hang out in the liquid. This talk is actually one that I put the slides together for just before Christmas for a conference at JPL. The flight software group at JPL runs a conference every year for everybody that does space flight software. And a bunch of years ago, I was a visiting scientist at JPL. I was really a kibitzing scientist. They were doing a project to do a next generation rover, which his Bushness pulled funding on because we had to go to Mars. I was like, asshole. Like he was actually serious, right? But so I got really, kind of into this, and I was really disappointed when that project went away. And then I met up with these guys who had done this funky robot that wandered around in the ocean, and they said, "Well, we're doing a new one, and it needs software. You want a job?" And I gave the obvious answer. So it's not your typical robot. It has no arms, no legs, no wheels, nothing like that. It's got a float that floats on the surface, and then a piece that hangs below. So you can see this. We usually call it either the sub or the glider. It's the thing that it sort of dangles on the end of this umbilical that connects the float and the sub, and that's me. And it's powered by the waves rather than anything else. So it started as a thing in 2005. A guy named Joe Rizzi, who was at Fairchild in the early days and spent a bunch of years as a venture capitalist and made enough money that he doesn't have to do much of anything other than whatever makes him happy. He has a house on the Kona coast, and sitting out in his backyard, and there's whales jumping, and he sort of says, "Well, I want to listen to them as well as watch them." And being an electrical engineer, he did the obvious experiments of, paddling out in a boat with a microphone and dropping it in the water with a long wire and discovering why that doesn't work. And he did all kinds of screwing around. And at some point, he decided that what he wanted was an RC car. And so he had a friend of his, Derek Hine, and his son, Roger. They started playing around with things because they were just trying to make an RC car for the ocean, and then they ended up with sort of the first version of this robot, Joe was one of the supporters of this outfit called the Jupiter Foundation. If you go to their website, jupiterfoundation.org, and I think it's still active now. Every year in whale season, if you go to jupiterfoundation.org, you can hear live streaming whale song. And if we had better sound here, I would have plugged in, and you could listen to live streaming whale song coming off of one of our robots. So they have a couple of our robots that go marching around, and they follow the whales, and unlike the tour boats, they can actually stay out there all night and just sort of wander along, and it's really pretty amazing to listen to. But then they got to this point of, well, this thing actually works. Can we turn it into a business? And then they started making things that were real robots and not just toys. So how it fundamentally works is we've got this two-part vessel, the float up in the top, a long umbilical. It's typically 7 meters. We do them in different sizes for different situations, but 7 is fairly standard. And then there's this glider piece down at the bottom, and it's got these wings, right? So in the this, you can see the wings sticking out on the side, and the wings are on hinges. And it's a really simple mechanism where you've got a wing on a hinge, as the float is up in the waves, the sub is down where the sea is calm, right? So if you've ever gone snorkeling, you're being tossed around in the waves, then you dive down, you go down not very many feet, and the ocean is calm. So this puts the wings down in the calm part of the ocean. The float bounces up and down in the waves. The sub gets pulled up and down, and the wings have a little hinge on the front end, so the whole wing just sort of flaps up and down, up and down, up and down. And there's like a little spring thing, so it just goes up and down like that, up and down, up and down, up and down. And that generates thrust. Generates a surprising amount of thrust. 700 or 800 pounds of thrust out of a standard wing ram. These things don't go very fast. What I've been playing with, and I'll demo, has been doing about 2.5 knots. So it's kind of a pleasant stroll, but it's the motor that never quits. It needs absolutely no fuel. You can go a long way if you just keep walking 24/7. So we've taken these things across the Pacific Ocean, across the Atlantic Ocean, up to the Arctic and down south of the equator. They've been all over the place. And if you're just persistently going, it just doesn't take you very long. One of the interesting things about the speed that we go at, so these things are fundamentally platforms for sensors, right? You can bolt kind of anything you want onto them. You can bolt hydrophones, current sensors. By that I mean water current, not electrical current. Fish sensors, cameras, all kinds of stuff, weather stations, whatever. And you can pull them through. We do lots of stuff with like water chemistry, doing like pollution monitoring around oil rigs. But mostly when you go out in the ocean with a ship, ships are expensive, and they really don't want to go slow, because going slow in a big ship is really expensive. Whereas a knot or 2 knots turns out to be really good for most scientific instruments. If you take most scientific instruments and you drag them through the water at 10 to 20 knots, they don't measure anything very well. 1 to 2 knots, almost all science instruments are very happy. So we can do, big global warming studies in the Arctic, or salinity studies in the Atlantic, or all kinds of stuff. And it turns out to be a really nice platform for scientific instruments. And in the only actuator, you guys do these robots that have got, stepper motors here and all kinds of weird stuff. We've really only got one actuator that counts. That's the rudder. The rudder is the only active thing. That our whole thrust mechanism, the thing with the wings and such, is completely passive. I mean, it's literally hinges and springs and carved fiberglass. It isn't exactly fiberglass. It's a little weird. But almost all of the dynamics of the vessel are completely passive. There's the only actively controlled surface on the whole thing is the rudder. Now the new ones actually have a thruster on the on the sub, but this thruster is very rarely used. It's only used when we get into trouble, like when there's another ship charging and there's a collision imminent or something, because the thruster heats up the battery pretty fast. So we do a lot of our communication using the Iridium satellite network. We're close to shore, which we usually are if we're doing like engineering tests. But for most actual science work that we do, we're way out of range of cell phones. And when you're in the middle of the Pacific Ocean, there's really not much there. It's literally millions of square miles of nothing. And the only communication channel that really works is the Iridium network. And the thing about the Iridium network is that it is expensive. It is expensive. It's $1 a kilobyte, right? Which is much worse than Comcast, right? People ask me, well, you have like some kind of a fancy big data solution. What do you do in your back end to handle big data? And it's like, well, $1 a kilobyte. That's like the maximum we can do, right? So you go to Fry's and you buy like a 4 terabyte drive, which costs you almost nothing. So at the time we fill up our first disk drive, we'll have blown $4 billion on satellite fees. At which point we can like launch our own satellite network, and who cares, right? But we're a long way from that. And even at cell phone rates, it's really hard to generate great gobs of data. And a lot of what we do is about living with the reality of a network link that is really, really, really slow and really expensive. It's almost literally text messages. We get about 300 to 400 bytes that we can send a minute. We don't do that very often. We try to keep it as sparse as possible. And when it comes to things like packet marshalling, how do you think about your network protocols? These days when people talk about compact versions of JSON or any other network protocols that people use, they worry more about making the data compact and not the metadata, all the header fields. And when you think about when data costs you a tenth of a cent for every byte, you fuss about every byte because they actually matter. Because it doesn't take, you don't have to save many bytes to have totally made up your salary. So it's a really different networking environment. We have different durability issues. This was an interesting discussion at JPL because they have to worry about all kinds of things. But we have to worry about ICs, for example. We put a lot of work into making these things really, really durable. So the worst storm we've been in is in a Category 4 hurricane. And so these charts here from one event just off of Australia, the peak that goes up to 90 knots there, this peak right here, this is a lie because the wind speed device we use saturates at about 50 knots. It's not capable of measuring beyond 50 knots. And it's like, well, why don't you just buy a wind speed sensor that does better than 50 knots? And the answer is nobody makes them. Why? Because these go on ships, and there's no ship out there that's going to survive more than 50 knots. So for all the people that make these instruments, there's no market for a weatherproof wind speed sensor that can handle 150 knots. It just doesn't work. So this one was going through in this event. This was 10 meter waves. We've been Had been through like 20, 25 meter waves and survived. But often it's not actually the height of the wave that's interesting. It's the slope of the wave face. So we had a series of incidents just 2 weeks ago where we had very high winds, and the waves weren't very high. They were like 5 meters, which is still pretty high, right? I mean, 5 meters is up there someplace. But the period between waves was like every 6 seconds. I mean, these were like standing up walls just flying, you know, the shock loads and all on the whole system are pretty terrific. So salt water, right? How long would your robots last if you threw them in salt water? Salt water is just so ugly. It affects everything, and especially if it's salt water for months and months and months. You know, so for instance, most stainless steel enclosures don't actually do very well if you leave them in salt water for many months. There's this phenomenon called crevice corrosion that affects stainless steel that in the previous generation was causing us no end of pain. You know, we'd have something that would be out in the ocean for like 5 or 6 months, and then, you know, it would lose contact with the rudder, and we'd find these little pin crevices. And doing a rescue in the middle of the Pacific is expensive. The only one we've actually rescued was done by a University of Hawaii ship. So we do a lot of titanium, a lot of weird composites. You know, the mechanical engineers get to have a lot of fun with really strange stuff that mechanical engineers normally don't get to play with. And we have to actually worry about sharks. You know, we're in a place where we get attacked. So we've only had like three shark attacks. This is one that happened not too far offshore from Maui, and if you look at where the scratches are, this guy's mouth was really big, and he mostly just scratched the paint, except that we had one place where we had a cable that went around. There's a shock absorber here, and the rudder mount is over here, and there was this one piece of exposed cable that went over this hinge, and if you can see there's a nick from a tooth, and that cut the wires going to the rudder, and we lost control of the rudder, and so it drifted. And fortunately, it drifted towards Maui, so we could go and pick him up. But it's an interesting engineering challenge to build a device that is designed to fit in the mouth of a shark and not damage the shark or the robot. It's quite different. So what do you do with these things? One use is you can use them as weather buoys that install themselves. There are weather buoys in the ocean all over the world, not nearly as many as you might think, because they turn out to be really expensive. So if you want a ship that's able to go and install a deep ocean buoy, costs about $150,000 a day just to rent the boat, right? So 1 day's rental is roughly what it costs to buy one of these, right? So like there's this big array of weather buoys across the Pacific called the Tau Array, and they're used for measuring a lot of the Pacific effects that lead to El Niños and a lot of the weather that affects California. Tragically, our beloved Congress 2 years ago defunded the last repair ship. So the tau array is rather quickly going dark. But one of the buoys in the tau array came back. It's not a buoy; it's one of our guys. And we've done it in a number of other places. Since we survived hurricanes pretty well, we've had a fair number of them in the Gulf of Mexico and in the Atlantic underneath hurricanes. We're really the only data source underneath hurricanes, which is kind of cool actually. If you look at like maps of the Gulf of Mexico when a hurricane goes through, all these ships, you see all their from their radio beacons, you see them running towards harbors, and our little guys are sitting out there alone. And the hurricanes go through and they go, waves, yeah. We do pollution monitoring. We wander around oil rigs in the Gulf of Mexico and wherever else. We've done a number of global warming studies for people. We do various things with C4 sensors. So for example, one area that the people are really interested in is tsunami warning. So tsunami is a very large wave, but they're not very tall, right? The wave height of a tsunami is like a meter or two. So if you're just floating on the ocean and the normal swell is like 3 or 4 meters, it's really hard to detect a tsunami just by the ocean going up and down. And also the tsunami is very broad as a wave, a very, very high wavelength. So it's really hard to detect. However, if you're on the bottom of the ocean, and if you have a sensitive gravitometer, it turns out that there's so much water moved by a tsunami as it passes overhead that you can detect the distortion of the Earth's gravitational field. It turns out it works really, really well. This has a problem. It has to be on the seafloor. How do you talk to something that's on the seafloor? Standard practice is a really long wire, right? So if you want to do tsunami warning for the coast of Japan, where they actually care about these things, you need like a wire that's like 1,000 kilometers long at least, and it's in the ocean. So it's the lifetime of a cable in the ocean is relatively short, and the vast majority of the world's tsunami sensors are working happily. They're just talking to nothing. And so what the people who really care about it do is that they actually have ships and they park over top of the tsunami sensors, and they use acoustic modems, just like the old phone modems. I mean, you listen to them and they sound just like a phone modem. And so acoustically, you can get several thousand meters in water. So so communicating between the surface and the seafloor acoustically works great over distances that are roughly the depth of the ocean in most places. But if you do it by taking a ship and parking over top of the seafloor sensor, in the places that are interesting, the ship costs you $150,000 a day. That gets really expensive really fast, and almost nobody except the Japanese care enough to do that. Certainly all around Hawaii, there are people who would care, but there's nobody going to pay $150,000 a day for one sensor, right? And then you actually need like dozens to actually make a difference. But our little guys can park overhead and have a modem. Our guys are happy to swim out from shore, swim out, a few hundred kilometers with an acoustic modem, do donuts for a few months, and then head back when you want to like scrape the barnacles off. Yeah. So what am I doing? So I'm working on this next generation robot that has got a thruster and more power, and it's got a real processor on it. And we put a lot of work into more advanced autonomy and doing work with to try to have large groups of these things. I mean, right now we've got about 300 of the old model and about 50 of the new model in existence. How many of them are in the water, I don't actually know, a good number. And so the new model is we sort of committed one of the worst engineering errors ever going from one model to the next, namely redesigned absolutely everything. There's like one or two small pieces that are actually the same, and kind of the shape is vaguely the same, but it's a real processor. A lot more solar panels. All the materials are changed. It's got a thruster for emergencies. So this is the inside of the command and control unit. So the heart of it is this ARM processor. It's a TI OMAP something or other. On the ARM processor scale, it's pretty wimpy, and it's actually a fairly old board. A Raspberry Pi would run circles around this particular board. We end up with this board because it has many serial lines. And most people, serial lines have been dead for decades, except in the marine world where everything moves very slowly. And everything is based on, there's this marine instrument standard called NEMA. And it's crazy how many things speak NEMA. And sort of the old versions of NEMA that are, RS something or other. The new NEMA standard, NEMA 2000, allows you to use like CAN bus and a few other things. But I've never actually seen a non-serial line NEMA device. They're a real pain to interface to, and we end up with dozens of them. So we end up with needing lots of serial ports this generation of processor board, we didn't want to redesign the actual processor board. But it works fine. We've got about 1/4 gig of RAM. There's a flash drive on board. All of these circuit boards here, these are the power supply. Or rather, they're the controllers for the power distribution to all of the instruments. So we can measure current, everything. Everything is, ground fault isolated. We can do all kinds of balancing of current from here to there. And everything is designed to be incredibly power efficient. In many ways, it's a fairly, it's a giant power supply with a CPU sort of accidentally glued to the side. So we have this network architecture that involves the WaveGliders out on the edge of the network that talk through usually an Iridium satellite network to a ground station. If we're close to shore, like I said, it's a cell phone. It's a cell phone network. And then there's a standard sort of cloud infrastructure where the WaveGliders talk to data cluster nodes that are redundant and failover and stuff like that. Then we can have a variety of web applications and desktop applications and things that talk to this. And there are different kinds of apps that we have. Ones that take live streams of data. Ones where the science crowd wants to look at old data or do comparative studies or whatever. You can do sort of database query kind of things. But a lot of the hard ones are ones that do sort of real-time streaming of data. So on board, there are a series of dry boxes There's the main dry box up in the float is a thing called the CCU, the Command and Control Unit. And there are going to add other dry boxes for various payloads. I want to look at the clock to make sure it doesn't get dark in Hawaii. We're running out of time here. And then there's communication down in the umbilical, and down in the rudder module, there's another processor. Actually, there's a whole host of processors. There's the main ARM processor, and then there are all these little embedded processors everywhere. The electrical engineers can't actually make a circuit board without putting at least one processor on it. And we've got so freaking many processor boards. I mean, the rudder module has 3 processor boards, and it has 3 processor boards more because of the org chart than because it made sense from an engineering point of view. So the particular piece that I've been doing is this thing called Regulus, which is the command and control software that runs on the ARM. You can think of it as being kind of like some of the robot OSs, the open source robot OSs. We can actually use a number of their components because this is just a Linux box. But it's in the ocean. We don't have kinematic anything, and we really care about fault recovery. One of the things that's different about this robot is that when bad things happen to it, there isn't a human being there to pick it up and get it going again. So it's got like multiple redundant GPS units, multiple redundant compasses. A number of pieces are redundant. We manage failovers. We manage, if the GPS fails, we do various things to try to restart it. We try reprogramming the firmware. We will power cycle it. We'll jiggle wires where we can. But when you're a robot out in the middle of the Pacific and you don't have it, and your last GPS fails, you're in trouble. We've only once had the last GPS fail, so it's all written in Java. It runs on a version of Linux from Timesys. Nothing particularly great about that version from Timesys other than it was the only one that we could find that would work on this particular embedded board. We used the Java Virtual Machine from Oracle. The JVM has never failed. It's kind of weird. We get far more Linux faults than we get JVM faults. But then again, we've only ever tripped into one Linux kernel bug. And one of the big deals in this is that there's just this unbelievably gigantic collection of libraries out there in the Java world. Some of them fairly obscure, like there's a really nice library, you give it a latitude, longitude, and time, and it gives you magnetic declination corrected for the drift of the magnetic poles. And it's accurate. It's got like 5 digits of accuracy. I only need 2 of them, but it's kind of cool. And there's just this gigantic pile of these libraries. It's great. It's crazy. So if you look at the code in this thing, 10% of it is doing like the interesting fun stuff. 90% of it is what it takes to stay alive. Managing power, managing failover. We do things like we monitor the rudder, and we've got all these sensors inside the rudder for the position of the actual rudder, the rudder actuator, and then the motor that drives the actuator. And there are instruments on all of those, and we make sure that everything is tracking. And if it's not tracking, we get upset and try to take corrective action. And we get like crud crows everywhere. So we try to do things like flip the rudder every now and then to clean out the crud. And it's a platform that's designed to be extremely modular. You can build plugins in all kinds of areas in the system. So it's all designed around services with a sort of a life cycle menu. If any of you have ever written like Java app server code, the guts of Regulus looks a lot like that. And in fact, it's got it uses dependency injection, kind of like a Java bean in a web app, except that the injected dependencies not only give you pointers to these remote beans, but it also builds a dependency graph, so that when the system is booted, the services don't have like simple states like, you know, started and not started. There's a whole progression of the life cycle of the service and the life cycle of the device, and the services can go in and out of failure states. And if you know, one service depends on another service, so like navigation depends on the location service, then the location service sort of aggregates all of the GPS sources, and you get all these dependencies all sort of filtered together. And as the system comes up, it keeps all the dependencies sorted, and so that things don't come up until they're needed. But also when things fail, that causes ripple through failures in the dependency graph. You know, if you lose the last GPS, then the location service goes down. Then you lose navigation. And in some sense, the system is always booting. You know, it never stops booting. It's just going along. So if you look inside it, it looks a lot like a publish subscribe kind of thing, except that it's all done using pointers, so it's very, very efficient. And we have lots and lots of threads. And there are times when we connect to outside heavyweight processes in Linux for some of the sort of C code that people have. We have to do that to talk to like a CAN bus. So this is kind of the hello world service. So add WG service, WaveGlider service. There's a simple service that detects when you've crossed the equator. It depends on the location service, and when it starts up, it creates a listener on latitude, longitude, and time. When it gets started, it starts listening to location, and it just does the obvious thing with if the sign changes on the latitude, it puts up a log event. But this is really quite robust. Deals with all deployment, undeployment, the management framework, things like undeploying, getting close render. This one are pretty simple. But the real guts are this dependency, and then registering interest in events from the location service. And there's a pile of standard services. The service manager itself is a service. There's devices are also services. There's communications as a service. There's when you want to send information to the shore, you give the communication manager a bag of bytes, and it sends it. But when you give it a bag of bytes to be sent, it isn't just here's a bag of bytes, send it. It's here's the bag of bytes. It's got this priority, this urgency, and I'm willing to spend this much. And so what priority means is sort of where in the queue it goes. Right? So high priority things get sent before low priority things. Sorry, not urgency. Sort of priority importance. And importance is really about sort of like given this bag of bytes, how important is it to get to the other side? So that would be like a piece of science data, for instance, would be highly important. And where that comes in is if the data is being queued and you start to run out of resources, you throw away the unimportant messages before you throw away the important messages. And also various messages, their importance changes over time. So like the location of the vessel, the current location, which is a message that you send to shore every now and then, it's got a very high priority. But a few minutes later, it's an unimportant piece of data because it's now stale, right? And you've got another lat long sample. So you want to throw away the like basic engineering data before you throw away science data. And then the sort of price bid is like, how much am I willing to spend to get this to shore? And right now it's like literally an amount in pennies, because we sometimes use cell phone networks, sometimes use Wi-Fi, sometimes you have hardwired networks because you can come in and dock and jack in, and sometimes use Iridium. And you can't send an MPEG, well, you can send a JPEG image over Iridium, but a 1 megabyte photo will cost $1,000, and most people are not willing to spend $1,000 to get one JPEG file transmitted to shore. Every now and then, somebody, in certain cases, people are willing to spend $1,000 to get the JPEG across, but usually not. So there's a lot of detail under here. There's situation awareness, there's a notion of what your mission is, there's a whole navigation service. One of the things that I spent a lot of time on was autonomy. So this is a screenshot from a fairly funky tool that's a mission planning people use. This was an event that happened in offshore of Hawaii 6 or 8 months ago. So these X's, these are our WaveGliders, and we typically park them in boxes, and they just go around in squares. This is in our engineering test area, and we just have to go around and around and around and around. And we had 2 of them inside our area. This black line here is the border of there's a chunk of ocean, several square miles of ocean that Coast Guard has given us the right to do all our engineering tests in, and folks are supposed to stay out. And most people, these are things called notices to mariners. And mostly people stay out of these areas because you put if there's a notice at the Coast Guard saying wild killer robots with laser cannons, stay out. Most people pay attention. This vessel here was the Navy SEALs doing exercises, and they don't pay any attention to anybody because it is their universe. And this was a boat with divers on it who were doing Lord knows what, and they were just kind of goofing off. And these trajectories where it went off to the side here, this one where it kind of drifted to the side. Nobody commanded the robot to do that. They went and did that on their own. They used their RF sensors to sense the position of the SEALs. The SEALs came through and they just got out of the way. And one of the interesting things about this is that it shows you how there are different behaviors for different kinds of collisions. So you can see the SEALs were coming along right here, and they were pointed in this direction, and that was a pretty imminent collision. And so this robot went, pretty much perpendicular to the path of the SEALs boat. This one here, he just got a little nervous. He didn't have a collision that was impending, but they're given there's a parameter in the collision avoidance algorithm that says closer than about 600 meters get a little nervous, so they want to kind of stay away. So this one was just kind of staying away, and this one here was actively fleeing. So here's a simulation that chose autonomous behaviors. The control algorithm that we use is one that's often called a potential field, and I really love doing things where there are emergent behaviors. So in this case, each WaveGlider was given exactly the same mission, namely go to this line and stay away from your brothers. Right, so you can see that 4 of them are dropped in the water. They burst apart from each other, and then they head towards the line, but they keep a space from each other. And which one went where is somewhat random. So it depends on who got dropped in the water first. The first one dropped in the water, he'll go straight to the line. The next one over will go off to the side. And you see, there's this 5th one that gets dropped in. You see the 4, they line up 4 abreast, the 5th one comes in, and then the 2 adjacent to it, they kind of move out of the way. See, they moved out of the way to make it 5 abreast instead of 4 abreast. There was no programming to make that happen, right? It's just got 2 rules, right? Go on this line, stay away from your brothers. And that's all the nav algorithm knows, and that's just what it does. And so here's the same nav algorithm, only the 4 are dropped in a different place, and the 5th one is dropped in a different place again. And you can see how the 5th one here, he goes to the end, and then all the 3 of the 4 move out of the way. Here's a simulation that shows that it's the same scenario except the ship comes through, and you can see that that the WaveGliders get out of the way as the ship comes through. And I spent a lot of time simulating these things before I did it live in the water. But you can see that when this guy here, when he moves out of the way of the ship, the other WaveGliders around it, they change their spacing as well to try to keep a uniform density along the line. So we do all kinds of fault management. I think I've talked about this a lot. Lean heavily on the fault management stuff in Java, all the handling of exceptions, the memory integrity, the fact that you can't have a fake pointer. The try-catch blocks give you a really good way of doing fault containment. And I use class loaders and security managers to be able to load in sort of plug-in behaviors. You can define plug-in behaviors for all kinds of things. There's redundancy everywhere, and I just don't believe any instruments. I think I talked about this one already. Who cares about security? So the whole write once, run anywhere thing in Java has turned out to be pretty cool because we end up running this code, on an actual vehicle, on these sort of test brain-in-a-box things that we have. I actually can run a complete WaveGlider on my laptop and just give it a fake GPS and a fake rudder. We can run it in the cloud, usually for testing. We can run it in a simulator. And one of the things that I'm about to start doing is running the WaveGlider inside of WaveGlider. So if you've got one WaveGlider working with a fleet of other WaveGliders, you're trying to guess what another WaveGlider is going to do, rather than doing some elaborate computing of what the other WaveGlider is going to do. You just run the code for the other WaveGlider on the first WaveGlider. You give it the conditions that the other one is in, and just run it like a simulation. And it works really nicely. So timing and scheduling, it's not really tight real time at the top. Although it's somewhat tighter than you might expect. But we have this, we're in the ocean, right? And the ocean is really, really chaotic. And, a timing miss is equivalent to being hit by a wave. So we have to be able to cope with chaos. So in this particular case, we don't actually care really closely about timing. That's a long, long discussion, but most of the real-time stuff we have is on some of these little peripheral processors. So here's a video. One of the things that I sweated on a lot, and in many ways this is a really boring video, because if you look at the rudder, which is down here, and I actually have the thruster running, and I was holding the camera kind of shakily. But the rudder, if you stare very closely at the rudder, you can see it move, but it usually doesn't move very much. It tries to be very, very efficient, because every time you do like a big swing of the rudder, it costs you speed. But then there's this point where it does this maneuver, where it does a 360 spin. One of the problems with this design is that umbilical can get twisted, and trying to come up with a device that would allow the umbilical to swivel. We haven't found a way to build like a cable swivel mechanism that will survive a hurricane and salt water. I mean, the whole open ocean thing just makes things really, really complicated. So rather than doing a swivel mechanism, we spin the whole sub, and by flipping the rudder to the side and cranking the thruster up, we can do that. So this is a picture of me. I mean, any software job where debugging involves putting on a snorkeling mask, that's a good job. And I spent a lot of time out. Our testing range is on the Kona coast. I do a lot of. I've gotten really used to snorkeling, several miles offshore. Like the first time when you're in, as they say, the deep blue, where there is no bottom to the ocean, and when you get offshore, 500 to 1,000 feet of visibility is somewhat normal, and you can friends come swimming by. Usually it's mahi-mahi, but occasionally they're more entertaining. So we've got people like me who work on the engineering, but the guy who was holding the camera we actually have a professional diver who his job is to look where everybody else is not looking, and he carries a spear gun, and sometimes he pushes interesting creatures away, and sometimes he just comes back with lunch. So let's see if we can do a demo. Where are we? Whoa! Made more progress than I thought. So this is our testing ground in Hawaii. This is the Big Island. Our offices our engineering offices up here in Hawaii Harbor. This is an industrial harbor. There are no tourist facilities for miles and miles of here. Our building is right here, so we've got a couple hundred feet of wharf space. And just before I came over here, so this is the robot that I was going to play with today. This ship came over here, which is we had normally there are no ships that come through this area other than tugboats. And this afternoon, about 5 o'clock, this thing shows up. 4,000 tons of super yacht. So I sent this WaveGlider over here to sort of park near it. So this WaveGlider actually has streaming video. So let's bring up the video. So here's live video. And so it's mounted, pointed forward on this guy. Yeah, I mean, this is like one of the coolest ways there is to do a demo. You know, driving a robot live off the coast. So there's this. I also run a web server. It's actually a copy of Jetty. If any of you know, I actually run Jetty embedded in the robot. And so when it's within cell phone range, you know, for all of the sort of engineering maintenance stuff, you can do it all using Jetty. So these web pages are actually coming off the robot in real time, and one of the things that you can do is you can give it scripts. We used to actually used to have a Jython interpreter in there. Jython is unbelievably hostile to multi-threading. And I just gave up and wrote a new script interpreter. Script interpreters are easy. And it's vaguely Jython-esque. So where is he now? So he's actually kind of vaguely turning. Why don't we I will edit waypoints, new. Sorry. Oh, there he is. Yeah, so let's take him and we'll kind of drive towards the edit waypoints, commit. What? Where did it complain? Let's just make it go southeast. Yeah, so he's not moving real fast. Right now, what is he doing? He has been doing about 1.2 knots. He's now sort of coming around slowly. There are a bunch of sort of safeties on him to try to make him not turn too quickly. Come on, you're turning around, aren't you? I didn't get an error message, so it should be doing it. It's just going slowly. Well, why don't we cheat? finally made this corner. Yeah, so there we go. Let's get rid of that. And just to prove to folks at work that I really did this, so the camera that's on there is a really weird, funky the software on it is pretty bad, or rather, the guys who made the camera gave it to us before it was decently debugged. Oh, come on. Upgrade on him. But yeah, so he's going to try to turn around again. I'm going to try to do that photograph again because he actually snapped the shutter just as the yacht was going out of view. And as you can see, the sun is getting ready to set. So it's 9 o'clock here, so it's 6 p.m. there, which is roughly around sunset. So I am not actually faking this. All right, we're coming around again. All I want is one Mega Babe yacht shot. Yeah, when you look this boat up, it's like owned by people who are just crazy. Come on, you're coming around, aren't you? Come on. Is he not? Damn. Well. Well, it does that because it momentarily focuses on the water drops on the lens cover. So anyway, it actually works. So I'm just gonna tell him to go home. Yes, he is going back home. So he's now going back to his home, his home parking area. So it'll take him a few hours to get back to where he normally parks because he's now swimming against the current. But so, questions?